Okay, I hope you are able to see the PPT. It is a root locus technique is the title. Is it visible to you?
Yes, sir.
Okay, thank you. So here the root locus technique. Earlier to this, we have seen Routh-Hurwitz criterion. There are certain limitation to the Routh-Hurwitz criterion. Some of the information is say cannot be obtained from RH criterion. So we'll go for the root locus. Probably nothing but we cannot get exact location of the pole in Routh-Hurwitz. So here we'll see the introduction, then concept of the root locus, then construction rule of the root locus. May few rules will be covered today, and later on tomorrow we'll cover certain construction rules. Then stability analysis of the system using root locus, concept of dominant closed loop pole pair, root counter effect of addition of open loop zeros and poles. These are the point under this title. Now, root locus, introductory part. Primary aim of control engineer to design a control system that meets specification. Then stability of the system is also necessary condition that we know. Then analytical approach can be followed up to second order of the system. Then computation becomes very say hard. Therefore, while Routh-Hurwitz criterion can be followed up to some higher order of the system that we have already seen. Then drawback of RH criterion, it does not provide information about relative stability. We have seen in previous lecture, yesterday's lecture, we have seen an example of air conditioner. If suppose complex pole is located at say minus zero point 0.1 plus minus j suppose, then minus zero point 0.1 means it is very close to the imaginary axis, and if there is some disturbance or say power failure, suddenly it may go to the unstable region that is on the right hand side of the imaginary axis. Thereby relative stability is very important here, which may make system unstable. ये RH में नहीं मिलता है relative stability. Does not help in designing control system where tuning of parameter is important. Wherever we need to say tune say parameter like overall gain k, it is not possible in RH. Then again introduction example of this root locus. I have a system. It is of course the feedback or closed loop system. You can say K is the overall gain of the system. GS is the open loop transfer function, and H of S is the feedback, where RFS is the excitation or input and C of S is the output. The open loop gain K of the system shown can be tuned from minus infinity to infinity. This is gain, of course. It can be tuned from minus infinity to infinity. System performance varies with K. Of course, it will vary because there will be existence of K into the equation or transfer function. RH criteria can neither provide information about amount of overshoot, settling time, or nor can it tell about the system response with respect to open loop gain. A kind of drawback of RH, of course. The pole of closed loop system can obtain from characteristic equation. You know what is characteristic equation? It is denominator equal to 0. Then it is important to know how closed loop pole move in S plane as the open loop gain K is varied. Like I have S plane, somewhere here is the pole, and if I vary the value of K, that is open loop gain, then does it remain here or does it move towards say this direction, that is left side direction, or move towards right hand plane? So this we will be going to learn. Next, root locus technique. The locus of migration of roots. Of course, if K varies, parameter system parameter open loop gain K varies, then there will be migration of root or pole of the characteristic equation of S plane is called root locus. वो migrate कहाँ होता है? वो range निकालना, that is nothing but root locus. Root locus technique was introduced by W.R. Evan, and there are some set of rules or construction rules of Evans that will be learned later on. Root locus technique is graphical method for sketching the locus of root of the characteristic equation in S-plane as a design parameter of the corresponding system is variable. So this is some theoretical background. Now one example of root locus technique. Let us consider a second order system we are considering where g of s open loop transfer function is 1 by s plus s into s plus a. That means there are two poles, s is equal to 0 and s is equal to minus a. And h of s, that is feedback, is unity 1. That is the poles of the open loop system is that, you know, that we already have seen several times. S is equal to 0, by putting this s is equal to 0, by putting s plus a is equal to 0, you'll get a minus a. There are two poles. The characteristic equation of the system is as s square plus as plus k is equal to 0, where k is what? System gain. If this is the characteristic equation, then the roots of the equation will be complex conjugate. You can get this another example. You can say the roots of the equation will be complex conjugate. You will get two pole, that is s1 and s2, by this formula, that is minus a plus minus under root a square minus 4k divided by 2. So these are the complex. For positive value of a and k, the system is always stable and root line left hand side of S plane. That is a stable region that we know. Positive value means you can see here it is S plus A. S plus A is there. So S plus A is equal to 0. So S will be equal to minus A. That will be located in left hand plane of the S graph. The relative stability of the system depends on the location of roots. Of course, pole kahan pe hai on that. Desired transient response can be varied by varying open loop gain. We'll see what is the transient response, that you know always, of course. So it can be varied by varying open loop gain k. As open loop gain k varies from 0 to infinity, the loci of root S1, these are the poles, and S2 in S plane is explained considering three cases. अगर हम k vary करते हैं तो what happened to these loci or root or pole that has, say, three conditions here, cases we have. Your k is varying from 0 to a square by 4. Let's see, we'll see what is this because it is not mentioned here. I'll tell you this first. So I'll plot this. This is what real axis and it is imaginary axis. I have two poles. One is at 0. So one is at 0 and another is at minus a. Another is at minus a. So now here, if k varies from 0 to a square by 2, the roots are distinct. When k is equal to 0, then roots are s1 is equal to 0 and s2 is equal to a. If you put into the equation, which are the poles of the open loop system that we have already plotted here. This is what? S1 and S2. This is 0. This is S1 and this is S2 is nothing but open loop pole. So here in case 2, this will be again explained into the example. For k is equal to a square by 4, the roots are real and equal. That will be S1 and S2 will be a by 2. So if I have the value from 0 to like I'm varying the value of k, and now k is what? K is what? K is a square by 4, exactly at end point. Then what happened? Then this pole will move towards this direction, and this pole will move towards this direction, and both will meet somewhere here, and that location will be minus a by 2, exactly at half this one, due to the value of course k is equal to a square by 4, a square by 4. As the k varies from 0 to infinity, one root start moving from s is equal to 0, and second start moving from s is equal to minus a. दोनों मूव होते हैं in opposite direction, as I mentioned in earlier PPT, ग्राफ शो किया था, upon opposite direction, and at k is equal to a square by 4, both roots meet at minus a by 2, exactly half of the portion 0 to minus a. And third case, हमने कौन से केस दिखा है? there are three cases, 0 to a square by 4, उसमें से अगर 0 वैल्यू लिया है k का, then your poles will be open loop poles, that is 0 and minus a. If k value is exactly a square by 4, then it will be what? Both the poles will move towards each other and will meet exactly at the center, that is minus a by 2. And what about third case? If k is greater than minus a by 4, then the root are complex conjugate, and given by the equation, this is the complex conjugate equation, minus a plus minus under root a square minus 4k divided by 2. The real part remain constant, of course real part remain constant, and imaginary part of the k varies, thus the root moves along the vertical line, that is upward and downward. What happened? Three cases we have seen. If it is 0, then we have s1 and s2 positions of open loop transfer function. If there is k is equal to a square by 4, then it will be minus a by 2. And if I further move, that is greater than a square by 4, then what happened? This pole will go towards vertical direction, and this pole जो यहाँ पे आया था will go towards this direction. Means suppose at certain value of k, if complex conjugate is here, exactly you will get mirror image replica is here. If your complex for certain another value of k, if complex conjugate pole positive pole is here, then you will get exactly replica of this. Means towards this will be towards infinity, and there was again minus infinity. So that means if I vary the parameter k, I'm focusing on what? Overall gain. If I vary the parameter k from 0 towards infinity, your roots will be on this axis or this line. यहाँ पे कहीं पे भी हो सकते हैं. It will never be here or here or here or here. It will never be at another point other than this line. And this S1 pole will remain on this line only. It will not change the line. And whatever is the value of k, if a particular pole lies on this line, complex conjugate line, then exactly replica of that pole will be in opposite side of the real axis. Okay, then these are the three cases. Means ultimately what we are doing, we are providing the range. If k is 0, then what? If k is a square by 4, then what? And if greater than a square by 4, then what? Okay, now you can see here one of the example. There are two poles here. Similar to that, one pole is at 0 and another pole is at minus 2. Minus a is nothing but minus 2. Means what is this? This has a transfer function like 1 over s into s plus 2. Here 2 is nothing but A. So if value k is 0, then your S2 will be at minus 2, S1 will be at 0. If I vary the value k, so if k is say what, a square by 4, that is 2 ka square, 4 by 4 means if it is 1, then this pole will move towards this direction. This pole will move towards this direction. They will move to each other. And at k is equal to a square by 4, according to this example, you will get pole exactly at minus 1, because a by 2 is minus 1 here. So it is minus 1. But further, if your pole is gain is greater than a square by 4, then what happened? Then your this pole will go downward in S plane, and this pole, this 0 pole will go upward exactly in opposite side. And if for certain value of k, suppose greater than a square by 4, a square by 4 means what? Here a is 2, so 2 to the power 2, that is 4. 4 by 4 means it will be 1. Exactly at 1, your pole located at minus 1 value. But say I have say 1.5, k is 1.5, then you may use this equation for calculating complex conjugate. I'll not calculate here. You know how to calculate. I'll calculate complex conjugate, and you will get certain value of complex conjugate. Suppose you got pole location here, you will get exactly opposite mirror image here. If I have say k is equal to 2, you may get another value of k, and again the replica of that. So you can see, if I change the parameter open loop gain k on root loci, your pole will follow this, S2 will follow this line, your S1 will follow this line. It will not be beyond this particular graph. Let me run the video here. I have a small video, and what happened to that you can see. It is very small actually. I'll run this. Let me see. I'm going to play this. It is somewhat fast. On the top you can see the variation in k value. Variation in k value here. There is one pointer above. The k value is varying. Accordingly your pole, -2 वाला pole इधर आ रहा है, 0 वाला pole left की तरफ आ रहा है, and then -2 वाला pole goes down and 0 pole goes up. So your open loop gain is varied. In RH criterion you cannot get this location, but in root locus you can locate the pole if the system parameter varies. Moving to the next PPT, I hope you understood. Moving to the next PPT, indicating advantages of root locus, indicating the manner in which the closed loop pole and 0 should be modified so that response meets system performance specification. Knowledge of open loop system is sufficient to analyze behavior of the system. Detailed study of the closed loop system is not required. Then, of course, we are strict to the point root locus technique. Under that, system parameters and pole location. ये दो चीजों पे हम concentrate करेंगे. Let's consider the first order system. A general form of transfer function of first order system is given by, you know what is that? That is nothing but what GS is equal to K upon tau S plus 1, where tau is what? Time, where K is steady state gain. जो पहले इसमें हमने K1 लिया था, 1 by S into S plus A tha. Then here tau is time constant. The pole of the first order system is at S, that is minus of inverse of what? Time constant, that we have already studied in unit number 1, there we have studied significant and insignificant poles also. So influence says the speed response of the output, that you have already studied in my lecture as well as Dekker's lecture. So you can see here, this is an example, not for the above equation. There are 3 poles, that is S1, S2 and S3. Suppose on the real axis they are not complex conjugate. So tau1 will be this. You can see it is very shorter. So for this pole, the system response is faster. Then tau2 for this pole S2, the system response is somewhat slow, and slowest response in this graph is tau3, that is for S3. So you can see, if your pole is located far away from the imaginary axis, then system will be faster. And we have seen the significant and insignificant pole. One of the pole we neglected because of that, because the time constant means we have seen what reduction of transfer function or equivalent transfer function nikala tha humne. You please refer that, you'll get an idea about this. Now what about the second order system? Second order system, the general form transfer function of second order system is given by this, that is g of s is equal to omega n square divided by s square plus 2 zeta omega n plus omega n square, where omega n is the natural frequency and zeta is the damping ratio. So there are several conditions. For zeta is equal to 0, the system is undamped. You know what is undamped, underdamped. For zeta value 0 to 1, it is underdamped system. For zeta value 1, it is critically damped system. And if zeta value greater than 1, it is overdamped system. Let's see the example here related to root locus. Here you will get what exactly the root locus technique is by this graph. We are moving through the theoretical concept right now. Later on there will be example. You will be calculating all the values and you will be getting such graphs. System parameters and the pole locations. Now here you have one characteristic equation. Say this is the characteristic equation. Wait a minute. There should be S here. Okay. So you can see the characteristic equation of the given transfer function is s square plus twice zeta wn, that is omega n s plus omega n square. And if you calculate the root of this, of course it will be complex conjugate. Don't worry about the values right now. We are moving towards the concept of the root loci. So if you calculate, it will be minus zeta omega n and plus minus j omega n under root of 1 minus zeta square. So you can see this is what the real part, this is the imaginary part. Now this P1 is the point which is showing the positive imaginary part, that will be plus j omega under root 1 minus zeta square, this one, plus exactly opposite replica, that is P2 will be minus value of this, minus j omega under root 1 minus zeta square. And if you get the intersection of these 2 points by drawing vertical line, here will be pole, which will be, of course, which will be your real part here. Here will be your real part, and that real part value is nothing but what it is, zeta omega n on the left hand plane. That's why it is a minus sign. Now here, these are the poles located here and here, complex conjugate pole. But if I vary the system parameter, Does it remain here? Of course not. And if it does not remain here, where do they move? Where do they move, or where do they migrate? Getting that idea is nothing but a root locus technique. Let's have the computation here. I have cos of theta. Cos of theta is nothing but, कैसे निकालोगे cos of theta? This value is what? This value is theta omega n. This one, theta, sorry, zeta omega n. And what about this value? Sorry, this value is omega n. So cos of theta, it is simply mathematics, geography, you can apply. So cos of theta will be zeta omega n divided by omega n, and omega n get cancelled. Your omega n and omega n get cancelled, and it will be simply value zeta. So your cos theta is nothing but zeta. Therefore, theta will be cos inverse of zeta. Theta will be cos inverse of zeta. Now, can we say if theta is constant, zeta is also same? Yes, I want reply from your side. I'm saying if theta is constant, then zeta is also same or constant, not same, it is a constant. Are you with me or lost the signal? Yes, to move further, I need a reply. I said, if I have 45 degrees, suppose theta, and zeta will be having some value. What I mean to say, I'll repeat it. Okay. Now, here is your line, omega n. Your pole may lie here if we change the system parameter, may lie here, may lie here, may lie here. Now you can see the location of pole is changing, but omega n pe hai, this theta is not changing. Theta is not changing. That means what? Theta is not changing. That means your zeta is also not changing. For this complete line, omega n, your zeta will remain same. Okay. Now, what is tan theta? It is nothing but here 1 minus zeta square upon zeta. Now, if I change the value of zeta, for particular omega n, यहाँ पे जो show कर रहा है straight vertical line, this one, for particular omega n, theta remains constant. That why zeta is also some constant value, maybe any number. We don't bother about that. But if I change this value, what will happen? Your theta will also change. Now here, similarly, you can see I'm trying to vary zeta from 0 to 1. You will get different theta angles. I'm not calculating here. No need to calculate. If zeta is 0, it will be perpendicular. Sorry, not perpendicular. It will be on the imaginary axis here. If I increase zeta, it will go here. Again I increase, it will go here. Again I increase, it will go here. Likewise. Likewise. This is how it goes. So locus of poles with constant zeta. यहाँ पे zeta की वैल्यू, यहाँ पे zeta की वैल्यू अलग है, 0 है. यहाँ पे कुछ zeta अलग लिया है बढ़ा के 0.1 something. यहाँ पे zeta अलग लिया है. Likewise, with certain constant zeta, you will get these lines, these different omega n, say omega 0, omega 1, omega 2, omega 3, likewise up to omega n. But if you are trying to smoothly vary this zeta between 0 to 1, then what you will get? You will get semicircles like this. Of course, you'll get semicircle like this. Why not circle? If it goes in circle, it will go in unstable region, that is right hand plane. So you'll get semicircles like this, which is a stable region. What this graph shows? It is a locus of pole with constant omega n. Means here you will get an idea if I vary the system parameter like zeta or whatever k, your poles may lie on these lines only in the semicircle region. So this is how is the importance of root locus technique. And of course, by looking at the position of the pole, you can easily identify whether your system is close to imaginary axis. If it is close to imaginary axis, relative stability is less, because if there is a certain disturbance or noise or change in system parameter, it may jump into the unstable region. Like I have quoted example of AC having a pole at -0.1 plus minus j omega. So in that case, if power failure for say few seconds, then suddenly your pole which is near to the imaginary axis -0.1 can directly jump to the unstable region, that is right hand plane. So ये सब हम थोड़ा एनालिसिस कर सकते हैं सिस्टम का. Moving to the rules now. Evans, W.R. Evans introduced this root locus technique in 1948. There are certain conditions called Evans condition. This is the closed loop system with system gain K, open loop transfer function GS, feedback H of S, RFS excitation, C of S output. The closed loop transfer function is given by, कैसे लिखते हैं हम standard form, that is transfer function is equal to gain into open loop transfer function divided by 1 plus y plus, because there is minus here, feedback negative दिया है, so 1 plus k into, because this k and these are the having multiplication, k into gs into h of s. So this is the numerator, q of s is the characteristic equation, is nothing but the denominator, where p of s and q of s are polynomials in s and k variable parameter. What this is, q of s and p of s is polynomial in s and k is variable parameter, and k may move from 0 to infinity. Now whatever we had seen, the theory will come into the picture in this example. Now the closed loop transfer function we already have on previous slide. Then what is the characteristic equation of this closed loop transfer function? Is nothing but qs is nothing but 1 plus kg s hs equal to 0. This can be written in adjusted form. 1 goes here towards 0 side, therefore it will be kgs hs equal to -1. This is second equation. Very easy, no need to further explanation. Since s is a complex variable in equation 2, can be rewritten in polar form as magnitude of characteristic equation, that is p of s, and angle of characteristic equation, that is p of s, angle of p of s, in the form of real part, that is -1 plus j0. यहाँ पे angle दिया नहीं है, so -1 is real part, j0. This is equation number 3. It is necessary that magnitude of p of s should be 1. This is called magnitude criterion. We will be using this, okay, later on. And angle of p of s will be multiple of 180, multiple of 180 degree. Equation is plus minus, it may be minus or plus 2q plus 1, where q will be 0, 1, 2. Means if q is 0, then it will be 180 degree, odd multiple. If q is 1, then it will be 2 plus 1, it will be 3. So again, what? Odd multiple. So this is what called angle criterion, equation number 5. So your equation number 4 and 5 are known as Evans condition. Evans condition, magnitude एक होना चाहिए और angle should be odd multiple of the 180 degree. Consider a system with open loop transfer function in pole 0 form. Pole 0 form में you know what is the gain, then this is 0, 1, 0, 2 product form up to m. So m number of zeros are there, divided by poles, s plus p1 into s plus p2 into going on, it is s plus pn. N is the order of poles. The Evans condition for existence of point on the root locus. Point on the root locus means कोई भी अगर point लेते हैं, whether that point lies in stable region or root locus or not, that is that we have to calculate. Then what is the magnitude criterion? That we know, magnitude of characteristic equation should be equal to 1. Angle of characteristic equation should be by this criteria, angle criterion. Then applying conditions of equation 4 and 5 on this equation जो given है, we'll rewrite this equation into the magnitude form. You can see, no need to read. So we can say here k into product of I1 to m s plus zi, product of all the zeros into k, divided by product of all the poles into the system should be equal to 1. And the angle criterion के लिए angle of k gs hs, that is nothing but same characteristic equation, should be summation of all the angles of 0 minus summation of all the angles of poles, and that should follow this criteria, that is odd multiple of 180 degree. Let's go ahead. Every point on S, point S in S plane that satisfied equation 4 lies on the root locus of the system with open loop transfer function given in equation number 6, जो हमने already देखा है. This is equation number 6. I rewrite here. For every point S on the root locus, there is existence of K satisfying this condition. What is K? K is equal to product of all poles divided by product of all zeros. ये equation को modify कर सकते हम. This equation is modified. K अगर इधर लाया, right? ये टर्म जो है प्रोडक्ट वाले, ये इधर लेके गए राइट हैंड साइड को. सो k विल बी इक्वल टू इनवर्स ऑफ दिस, प्रोडक्ट ऑफ ऑल द पोल्स डिवाइड बाय प्रोडक्ट ऑफ all the zeros. This is the equation number 9. We'll be using these equations. So this is the example with some values. Now you will be calculating the root locus. Let us consider open loop transfer function, that is kgs hs is equal to k into s plus 2 upon s into s plus 1. Tell me how many poles and how many zeros are there in this equation 1. Yes, I want reply from your side. How many poles, number of poles, number of zeros? I'm waiting for the answer. If I don't get answer, I will extend the lecture until it finish, until I finish all the slides. There are so many slides there. Yes.
So 2 poles and 1 zero.
Right. Can you mention 0? 0 is at minus 2. 0 is at minus 2. Because s plus 2 is equal to 0 अगर लिया तो s जो 0 है z1 will be at minus 2. What about one pole? One pole s is equal to 0 and another pole is s is equal to minus 1. So let s0 be, ये यहाँ पे लिखा है हमने, ये 0 है at minus 2 on the diagram, ये pole है at minus 1 ये 0 वाला पोल हियर, ये -1 वाला पोल हियर, देन -2 पे 0, 0 सर्कल से दिखाया है। अभी हमने क्या किया है यहाँ पे, आई हैव लोकेशन ऑफ पोल एंड 0, बट आई विल चूज एनी पॉइंट ऑन द ग्राफ, ये पॉइंट, ये पॉइंट, ये पॉइंट, एनी. So I have chosen this point, say S of 0, S0, and joined all the poles with that S0, and I am trying to find out whether this S0 is on root locus or loci or not. So let S0 be a point on the root locus. Therefore S0, the point S0 satisfies the angle condition given by equation number 8. What is angle condition? Summation of angle of all the zeros minus summation of all the angle of the poles, and it should follow this value. Okay, then in this equation let S0 be a point on root locus. I repeated this. And what about another condition? If the parameter k is given, k should be what? Number of poles, product of number of poles divided by product of number of zeros. So what are the number of poles? This A line, this B line. So I have AB divided by 0 key line, this C line divided by C as shown in the figure. This should follow the what gain criteria, that is equal to 1. Then we can say that it is on root locus. So here there are several rules. I think there are 6 rules, out of which we'll see only 3 rules today, looking at the time. So construction rules are there. Construction rule 1, 2, 3, 4, 5, 6 likewise. So I'll read it. The root locus is symmetric about the real axis, and the number of branches is equal to the order of the characteristic polynomial, that is number of poles of the open loop transfer function. जितने number of poles है उतने number of branches. The root of characteristic equation are either real, of course it may be real, imaginary, or complex conjugate, or combination of all. कुछ भी रह सकता है रूट्स, जैसे कि -1, -2, it may be -0.5 plus minus j2, or combination of this. The root locus above the real axis is mirror image of root locus below the real axis and vice versa. That we have already seen in earlier example. If I have S-plane like this, if I have complex conjugate pole here, there will be mirror here. If I have here, then there will be mirror here. If I have here, it will be mirrored somewhere here. So this is the statement. These are some points to be remembered. It is in theoretical form, of course. The number of branches of root locus is equal to order of the characteristic polynomial, that we have already mentioned in the definition here. Construction rule 2. All the branches of root locus at open loop poles when k is equal to 0 and ends at either open loop 0 or infinity. जितने भी branches है, it start at open loop pole and ends at open loop 0. ग्राफ है वहां पे आपको समझ में आ जाएगा. The number of branches terminating at infinity is equal to difference between number of poles and number of zeros. Let's have an example. If I have one number of pole and one number of zero, then suppose this is pole and this is 0, then there will be only one branch starting at pole, and I'll use pointer instead. If I have pole here and I have 0 here, one pole, 1 0, and this pole will originate one branch and will terminate here. This is the case of one pole, 1 0. Let's have another example. I have two poles, real axis nikala nahi maine. Suppose real axis pe I have one pole here, then another pole here and another 0. Then what happened? One branch will originate, terminate at 0. Another branch from this pole terminate at 0. So here number of poles are 1, therefore one branch. Here the number of poles are 2 in this example, therefore there are 2 branches. What if I have only one pole, sorry, 2 pole and 1 0. I have one pole here, I have one pole 0 here and another pole here. Now what I have number of pole 2, number of 0 1. So यहाँ पे your branch will start here at pole and will terminate at 0. What about this? As there are 2 poles, there will be 2 branches. This first branch will terminate at 0. What about this branch? Will move towards infinity. And same is given in there. Here, number of branches terminating at infinity equals to the difference between number of poles and zeros. यहाँ पे poles and zeros का difference क्या है? 2 minus 1, it will be 1. So there is one branch. It is unending, terminating at infinity. So the characteristic equation I have, no need to read it out, is equal to 0. It is rewritten like I have multiplied this denominator with this 1. So it will be product of all poles plus k into product of all zeros equal to 0. Modify किया है equation number 2 को. This adjustment. In equation number 3, all points for which the left hand s-plane or left hand side is 0 lie on root locus. Let's say for value of k is equal to 0. Then what happened to this term? This term becomes 0. For value of k is equal to 0, this term becomes 0 and all the poles will be located on left hand side of the s-plane. Let us consider k is equal to 0 in equation number 3. Then equation becomes that product of all poles is equal to 0. This term vanishes. The root locus of equation number 4 is this one, are nothing but the poles of the open loop system. Thus all open loop poles are the part of root locus and all branches of the root locus originated from the open loop pole. जितने भी पोल है उतने ही branches वहां से originate होंगे. Then now in equation number 3, I have just modified this equation number 3. K से divide किया है. So 1 by k, product of all poles plus product of all zeros equal to 0. Now I will take value of k infinity. Let us consider k infinity. Then what happened? If k is infinity, then this term becomes 0. Pole wali term becomes 0. And the equation 5 becomes product of all 0. Magnitude of product of all 0 is equal to 0. In equation number 6 shows that all open loop zeros lies on the root locus branches and these open loop zeros are terminating points of root locus branches. जितने भी poles से branches निकल रही है, that will terminate at 0. And if there is a difference, then few branches may terminate at infinity. In most of the system, the number of open loop pole is greater than number of open loop zero. हमने देखा था इससे भी पहले first unit में. M is greater than N. So only M poles terminate at open loop zeros. What about the remaining N minus M? So N minus M, they will terminate at infinity. हमने earlier example देखा है, अगर दो पोल एक जीरो है तो एक पोल जीरो पे टर्मिनेट होगा, another जो डिफरेंस है that will terminate at infinity. Just two more PPTs. We'll see the construction rule 3 and then we'll end this lecture. At a point on the real axis, एक दिया है directly S plane. Forget about the characteristic equation. How many poles are there? You can see P1, P2, then P3, P4. There are 4 number of poles. Let's see the 0. There are Z1, Z2, and Z3 and Z3 dash is a complex. So there are total, including complex, there will be 3 zeros. The root locus, if sum of the poles and zeros of the real axis to the right of the point is an odd number. Let's see this. Angle of all, that is angle of, हमने क्या किया, एक पॉइंट डिसाइड किया है यहाँ पे ग्राफ पे, एंड वी आर लुकिंग whether this S0 point lies on root loci or not, or loci or not. So for that सभी के एंगल निकालने पड़ेंगे. Angle of P1 is equal to angle of P2 is equal to angle of Z1. कैसे निकालते हैं? इधर का पार्ट नहीं लेना है हमें, हमने ये पॉइंट लिया है. We will consider only this side, that is right of the set point. S0 का क्या कहते हैं हम? It is a set point. Right of the set point, and right of the set point से हम एंगल्स देखेंगे. लेट्स सी P1 को अगर हमने एंगल लिया है ये सेट पॉइंट को, सो इट इज 180 डिग्री. ओके, P2 इज आल्सो 180 डिग्री एंड Z1 इज आल्सो 180 डिग्री. सो ये तीनों के लिए द एंगल इज 180 डिग्री. लेट्स सी एंगल फॉर अनदर. एंगल फॉर P3, एंगल फॉर P4, एंगल फॉर Z2 जो कि इधर है P3, P4, Z2, that is 0. That angle is 0. And what about angle of this Z3 and Z3 dash combinedly? So ऐसे एक लाइन हमने ड्रॉ किया है, यहाँ से यहाँ एंगल देख रहे हैं हम. So it is this angle, और सेम लाइन पे इसका एंगल अपोजिट. So if you sum these two angles, that will be equal to 0. So summation of the angle of Z3 and summation and Z3 dash will be 0 degree. ये हमें मिला है. Let's see the interpretation from this now. Sum of angle contributed by complex conjugate pole is 0, जैसे कि हमने यहाँ पे मिला है, क्योंकि एक एंगल ऐसा आ रहा है और एक एंगल ऐसा आ रहा है, इसका sum will be of course 0. Angle contributed by every pole and 0 on real axis right of the test point is 180 degree. आप देख सकते हो प्रीवियस सिस्टम में ये तीन जो है, एक 0 और दो पोल, ये टेस्ट पॉइंट के राइट साइड में है, उसका एंगल 180 डिग्री आता है. देन अनदर एंगल कंट्रीब्यूशन बाय एवरी पोल एंड 0 ऑन रियल एक्सिस लेफ्ट टू द टेस्ट पॉइंट इज 0 डिग्री. सिमिलर ये तीन जो है पोल एंड 0, इसका कंट्रीब्यूशन will be 0 degree. Sorry, not this one, 0 degree. And third, therefore the total angle contributed by the system whose pole 0 plot is shown in the figure of test point S0. कौन सा? ये वाला टेस्ट पॉइंट S0. इसके हम ऑल एंगल कंट्रीब्यूशन देखेंगे. सो ऑल एंगल P1, P2, P3, P4 का प्लस Z1, Z2 zeros का प्लस कॉम्प्लेक्स कॉन्जुगेट का समेशन Z3 एंड Z3 डैश का. पुटिंग इट हियर इट विल बी -180 -180 -0 माइनस फॉर्मूला में पुट करके +180 देन 0 इट कम्स -180. इसका सबका समेशन आ रहा है -180. एंड -180 क्या है? -180 मीन्स Q की वैल्यू क्या है? लेट्स गो टू द इक्वेशन सो इट विल बी इजी. Here -180 आया है, इसका मतलब Q की वैल्यू इज 0. मीन्स व्हाट इज मल्टीप्लायर टू द 180 डिग्री? दैट इज 1, and 1 is nothing but odd multiplier. 1 is nothing but odd multiplier. So here 180 -180 is the odd multiplier of this value, Therefore your S0 is a point of root locus. अगर ये odd multiplier आया तो S0 is the point of root locus. S0 is a point of root locus. Then another set point लेंगे हम. Let's see. I took set point S1. Same analysis हम इस पे करेंगे. Same system, but set point मैंने बदल दिया है S1. Now check the P1 angle. P1 angle is 180. P2 angle is also 180. Z1 angle is 180. P3 angle is 180. What about contribution of P4 and Z2? It will be 0. What about contribution of summation of Z3 and Z3 dash? Will be 0. So same values, interpretation. Sum of angle of complex conjugate pole is 0. Angle towards right of the test point is 180. तो कितने 180 है हमारे पास? 1, 2, 3 and 4. Angles contribution by every left of the test point is 0. कितने left में है? 2. So it will be 2 zeros. Let's do the same. Summation of all. So it will be minus 180, minus 180, minus 180, minus 0, plus 180, plus 0, plus 0. Just सबके summation कर दिए मैंने. So it will be what? Minus 360. And what angle criteria? Minus 360 means Q की value क्या है? Minus 360. So here minus 360 is the even 2 आ गया. 2 into 180 is 360. Even multiple of 180 degree. Therefore जो भी हमने set point choose किया था S1 is not a point on root locus. यहाँ पे पोल हो ही नहीं सकता. One example, numerical example, so that you will get all idea about construction rule 1, 2 and 3. Draw the root locus of the transfer function given. K s plus 1, s plus 3, that those are the two zeros, 1, minus 1 and minus 3 pe. Then s into s plus 2, s plus 4. There will be 3 poles, that is s0 pe, s minus 2 pe and minus 4 pe. So this is given here, no need to read. ये 3 poles है. So we'll plot that. We'll plot this. Poles कितने हैं? On 0, then minus 2 and minus 4. Where form we obtain this? From the characteristic equation of open loop. This is s is equal to 0, this minus 2 and this minus 4. What about 0? 0 is at minus 1 and minus 3. Let's put that. 0 circle से हम दिखाते हैं. 0 is at minus 1 and minus 3. No further poles and 0 are available. Then what will happen? The pole initiated at 0 will have, how many branches will be there? There are 3 poles, means 3 branches. So one pole initiated at 0, terminated at 1. That is, this value will be what? K is equal to 0 and this value will be K is equal to infinity. Another pole will initiate branch at minus 2 and will terminate at 0 at minus 3. Same, this will be K is equal to 0, this will be K is equal to infinity. But what about third pole? We do not have further 0. We do not have further 0 in this graph. So difference between pole and 0, that is pole 3 minus 2 0, that will be 1. So there will be one pole initiating a branch will not terminate it. It will be terminate towards infinite value. So here are the 3 branches because 3 poles are there. Whatever we learned till now will be clear. 3 branches because 3 number of poles are there. 2 branches will terminate at zeros, that is minus 1 and minus 3 because there are 2 zeros. But one branch will terminate as infinity because difference between pole and 0 is 1. Then your set point, your root loci, your set point may lie on this line, may lie on this line, may lie on this line system. It will never be here. It will never be here. So yes, of understanding is possible with root locus. So thank you very much. If you have any question related, you may ask. I'll give you half minute for that.